Okay, welcome everyone to this joint webinar hosted by HEC and CRM. This is part of the Colloque des Sciences Mathématiques du Québec series. It's my great pleasure to welcome virtually Daniele Durante, who is an assistant professor of statistics at Bocconi University in Milano. Daniele is a Bayesian statistician. He's been at Bocconi since 2017 after completing studies under the supervision of Bruno Scarpa at Padova, and working also with Dave Dunson at Duke University. Daniele is associate editor of Biometrica, GCGS, and Journal of Multivariate Analysis. He is particularly interested in Bayesian methodology with application in network problems and social science, working also with categorical data and computational methods. He has a great publication record in top journals in the field, and has been awarded numerous prizes, including the Laplace Prize, Leonardo da Vinci Medal from the Ministry of University and Research in Italy, and PhD Thesis Award. So Daniele, thanks a lot for accepting our invitation. The floor is yours. To participant, I would like to ask you if you have questions during the talk. Please don't hesitate to write down something in the chat, and I'll be monitoring it along. So if you have deeper question, we'll keep them to the end. But for any clarification question during the talk itself, please feel free to step in. Daniele, the floor is yours. Thanks again.
Okay. Thanks a lot, Leo, first for the invitation and for the very kind introduction. Let me also apologize for not being there in presence. Actually, I would have really loved to give the seminar in person there, but I'm still in the middle of the teaching semester. Okay, now going to the seminar of today, as you can see from the talk, what I will try is essentially, let's say, to show you the impact within Bayesian statistics of a broad class of distribution that arise from skew perturbation of multivariate Gaussian densities and more general of symmetric densities. This is a class of distribution which has been developed mainly to, let's say, model skewed phenomena. Much less attention has been devoted to the potential consequences that this class may have within Bayesian statistics. So what I will try to do today is essentially to go through a number of recent contributions that I did along these lines, but essentially really my goal is to show you that actually such a class, such families have a very fundamental impact within Bayesian statistics. So in particular, we will see, for example, that a subset of this class of skew-symmetric distribution actually act as conjugate priors for a broad class of statistical models that we often use in practice, like probit regression, multinomial probit, tobit models. And then more generally, going to more general statistical models and more general posterior distribution, what I will show you is that within such a class, we can actually find interesting skew-symmetric approximating distribution that allow us to improve the approximation accuracy of classical, let's say, symmetric or Gaussian deterministic approximation of posterior distribution. And we will actually do that through a simple perturbation of these symmetric densities that do not require us to do additional optimization step, but at the same time give us the guarantees of improved accuracy in the approximation, both in finite-sample and in asymptotic regimes, keeping the same tractability of the original symmetric approximation. Finally, then we will try also to quantify, let's say, the gain in accuracy. And to do that, we will see an extension of the classical Bernstein-von Mises theorem that we have in Bayesian statistics. But essentially, what I will show you is that if we replace the classical Gaussian limiting distribution studied under such a theorem with a suitably defined skew-symmetric distribution, then we are able to improve the convergence rate by a square root n factor. So this is, let's say, the broad overview of the seminar. Let's start with the conjugacy result. And let me do that essentially by claiming the obvious, which is that we all like regression models, right? They provide us with a simple method and very starting good way to understand how the conditional distribution of some response variable or function or this distribution change with covariance. However, as we all know, also, anytime we go beyond regression models for Gaussian response data, things get a bit more complicated, either from a computational or inference perspective. For example, in the Bayesian context, This is because we typically lose the conjugacy between the commonly assumed Gaussian prior for the regression parameter and the likelihood induced by the non-Gaussian response data. And this happens even in very basic settings. For example, when we extend to, let's say, regression models for binary data like probit regression. So in this case, as you can see here, we assume that our binary data of condition-independent realization from Bernoulli random variables was probability are obtained by mapping a linear combination of the parameter into the probability space using the probit link, so the CDF of the standard normal. Then as Bayesian, we need an ingredient more, which is our prior distribution for the regression parameters. Of course, we have many options. A good starting one and a commonly used one is to go with a multivariate Gaussian prior for the regression parameter. Then in the Bayesian context, what we need to do now is to derive the posterior distribution, so the conditional distribution of the beta parameter given the observed data, and essentially perform inference by studying the properties of such a posterior. So to do that, well, we can just apply the base rule, right? So this will tell us that my posterior density for the beta parameter is nothing but the Gaussian prior times the probit likelihood divided by the normalizing constant, where essentially we marginalize out the beta parameters from the probit likelihood according to the Gaussian prior. Now, what we do at this point is to look at this formula, in particular the numerator, and hope to recognize the kernel of some well-known or at least tractable class of distribution, which doesn't seem to be the case in the probit regression. It's even not clear where we can identify a closed form expression for the normalizing constant, so for the marginal likelihood. So what's the option at this point? Well, we can leverage all the machinery that we have in Bayesian statistics to perform inference under intractable posterior distribution. So for example, we can go with sampling-based methods like Metropolis Hastings, Gibbs sampling, Hamiltonian Monte Carlo, or we may just be happy with a deterministic approximation of my posterior distribution, which is much more tractable than the posterior itself, but at the same time is hopefully as accurate in approximating such a posterior. So these are clearly all state-of-the-art methodologies, which have been nicely reviewed in this article by Nicolas Chopin and James Ridgway, where they also claim that still, of course, even if they are state-of-the-art, they face some open problems, especially in high dimension, for example, in terms of mixing of the sampling-based methods, or for example, in terms of the accuracy of the approximation for the deterministic ones. Of course, what I will stress here and add to that is that these methods are, of course, also still suboptimal compared to situation in which my posterior distribution is available in closed form and belong to a known class of distribution. So this brings me to the very first result of this seminar. In particular, what I proved recently is that actually the posterior distribution in probit regression with Gaussian prior belongs to a known class of distribution. So such a class is the unified skew-normal class. Okay, so what are unified skew-normal distribution? Well, it's a broad class that has been developed by Arellano, Valle, and Nazzalini, essentially to unify several different extensions of the original multivariate skew-normal distribution, whose density, as you can see here, is obtained by perturbing the one of a p-variate Gaussian with a skewness-inducing mechanism driven by the CDF of a standard normal distribution evaluated a linear combination of the values of the variable. So this induced skewness within this original symmetric density, and that's been extremely popular in modeling skewed phenomena to the point that later on has been extended in several directions. Some of these mainly also to recover the closure properties that the original multivariate Gaussian distribution has. So what Arellano, Valle, and Nazzalini did was essentially try to unify all these different extensions within a single class that was named unified skew-normal distribution, which, as you can see here, is indexed by two-dimensionality quantities, P and Q, and then by a number of parameters, which essentially control the location, the scale, the skewness, and the dependence within such a random vector. So here I won't stop too much into the meaning and the role of these different parameters, because later on we will see those coming from our unified skew-normal posterior from probit regression. What I want to show you here is just the density of such a random variable, because inside that is essentially contained the conjugacy result that we will see later on. So the density, as you can see here, is the one of a p-variate Gaussian multiplied by the CDF of a q-variate normal distribution, still evaluated the linear combination of the value of the variable, and then divided by the CDF of another q-variate Gaussian, which is essentially our normalizing constant. Now, by looking at this CDF, at this density, if you recall the Bayes rule that we applied before, you can really see already why this might be the posterior distribution in probit regression. Because this might be just my Gaussian prior. This may be just a way of rewriting my probit likelihood. And here I have just the normalizing constant that will be available as a byproduct of that. So to go more into the detail of this conjugacy result, so what it proves is that if we have probit likelihood, a Gaussian prior, then my posterior distribution is a unified skew-normal with dimension p and n. So p is the number of parameters that I have, n is the sample size. And as you can see here, each parameter can be obtained as an explicit form from the prior mean vector C, the variance and covariance matrix omega of the prior distribution, and then the data which are contained in this matrix D. So this is nothing but my design matrix where I change or not the sign to the rows, depending on whether the associated response is 1 or 0. So as I was promising before, again, the proof is very simple. You just need to apply the Bayes rule and write your posterior density as proportional to the Gaussian prior times the probit likelihood. This is nothing but a way of rewriting the probit likelihood. So because it's a linear combination of my beta parameter with a diagonal covariance matrix so that it will factorize as the product of univariate CDF. Once you are there, you just need to do some simple linear algebra operation to highlight the unified skew-normal parameterization. So that's basically the simple proof of the result. Clearly, the second question is this result just a curiosity, or is it also useful to perform inference and computation? Well, it's also useful in the sense that unified skew-normal distribution, as I was mentioning before, inherits several closure properties of the original multivariate Gaussian. So in particular, unified skew-normal distribution are closed under linear combination, marginalization, and conditioning. So this means, for example, that the posterior distribution for each of my beta parameter will be itself a unified skew-normal. The other aspect, as we have seen before, is that unified skew-normal distribution have a known normalizing constant, which we can compute. So this will be the CDF of an n-variate Gaussian. So as long as we can evaluate such a normalizing constant, then we can, for example, compute in closed form predictive probabilities or evaluate Bayes factor, which will allow us to perform variable selection. Finally, another interesting aspect is that unified skew-normal distribution have a very simple additive representation as a linear combination between p-variate Gaussian and n-variate truncated normal distribution. So as long as we can sample IID from these two variables, and we can do that, then we can now draw IID values from our posterior distribution and perform inference under any functional just using Monte Carlo, which is way better than relying on MCMC methods, because again, we no more have problem of mixing, no more have problem of convergence. And then finally, we also have a moment generating function available in closed form. So potentially we can also compute moments without relying on Monte Carlo integration. So these are the results for probit regression. At this point, the question is, that's the other interesting aspect. So the other interesting aspect that I didn't mention is that actually unified skew-normal is the conjugate prior to probit regression. So here we have seen that Gaussian prior combined with probit likelihood give me a unified skew-normal posterior. What you can easily prove now is also that any unified skew-normal prior combined with a probit likelihood give you a unified skew-normal posterior, okay? Which means that now we can also include skewness within our prior beliefs. So the question now is, of course, does this result extend beyond probit regression? So do we have other statistical models to which such a class of distribution act as a conjugate prior? So this brings us to the second result, where we actually prove that probit regression is just a specific case. Actually, unified skew-normal is conjugate to a way broader class of distribution, which are used a lot, for example, in econometrics, and in particular to any distribution was likely to factorize in the way that you see here. So was likely to factorize as the product of a Gaussian density evaluated a linear combination of the parameter and the Gaussian CDF evaluated the linear combination of your parameters. So anytime you have a likelihood of this form, then the unified skew-normal will be the conjugate prior to such a likelihood. This is a very general class of likelihoods because, as you can see here, if I put n0 equal to 0, I essentially go back to multivariate Gaussian regression models for, again, normal data. If I put n1 equal to 0, then you go back to the likelihood induced by probit regression, multivariate probit, multinomial probit. If both of the two survive, then you have, for example, tobit regression. So also here, the proof is pretty simple in the sense that what you need to do is first to update your unified skew-normal prior with the Gaussian density part. Here you will just have to leverage Gaussian conjugacy. That will give you an intermediate unified skew-normal posterior, which will then combine with the CDF part of your likelihood. And here you can again leverage similar result that we have seen for probit regression. So again, anytime you have a model which arises from tobit regression, multinomial probit, multivariate probit, and so on, then you know that your conjugate prior will be the unified skew-normal. So if you combine that with that likelihood, you will have a unified skew-normal posterior whose parameter can be again obtained in closed form. So this could conclude the seminar essentially, in the sense that I showed you all these conjugacy results. I told you that the class of distribution is known. I told you that we can sample IAD from that. We can potentially evaluate the normalizing constant. There is a problem, of course, which I was not stressing too much before. The problem is that, as I was mentioning before, inference under such a unified skew-normal posterior requires that we are able to sample from n-variate truncated normal distribution with full covariance metrics, or that we are able to evaluate CDF of n-variate Gaussian distribution with full covariance matrix. So this is actually a challenging task as n grows. So therefore, later on, now we will see some solution. This doesn't mean clearly that these results are not useful in the sense that nowadays we have several advancements which allow us to evaluate Gaussian CDF and sample from n-variate truncated normal distribution as long as the sample size is in the order of few hundreds. As n grows, then these tasks start becoming challenging. So actually this problem then brings me to the second part of the seminar. Well, the idea is, well, if we have this problem as n grows, let's see what we can do. So let's see in particular if we can come up with an improved deterministic approximation of our posterior, which actually now improves the state of the art that we now have in probit regression, knowing that my posterior distribution is a unified skew-normal. So that's the idea. So the idea is as n grows, then inference under the exact unified skew-normal posterior become more problematic from a computational perspective. Then the question is, can we, let's say, come up with a deterministic approximation of such a posterior, where this deterministic approximation hopefully will also improve those that we have from the state-of-the-art studies in probit regression, because now we know that our posterior distribution is a unified skew-normal. So to do that, essentially, we will see an improved approximation that comes from variational base. So to introduce variational base, let me first go through a very simple and widely used augmented data representation of probit regression. This has been popularized by Albert and Chip, and has been used a lot in the development of Gibbs sampling strategies and mean-field variational base approximation under probit regression. So essentially, this augmented data representation basically tell me that probit regression is nothing but a Gaussian linear regression on an underlying set of latent data Z, which, however, I do not observe. I only know whether they are above or below 0. So here, if you integrate out the Zs, then you go back to probit likelihood. Now, you can already see why this representation is useful, because in a way, if we knew Z, so if we knew the latent data, then we restore Gaussian conjugacy. So given Z, then my posterior for beta is actually independent from Y and will be a Gaussian distribution. Of course, I don't know. So here I restore the Gaussian conjugacy once I augment with the latent data. Of course, I don't know. I don't observe this augmented data, so I need to sample them as well from their full conditional distribution, which is also available in closed form, because if I know beta, then I know that Z is a Gaussian. And if I also know Y, I know whether it lives above or below 0, which means that the ZIs, so my augmented data, are univariate truncated normal distribution. And given beta, they are independent among each other. So here, essentially, you already have the step of a Gibbs sampling algorithm, because what I can do is now I can iteratively sample from this full conditional, and this will give me a stationary distribution, which is actually my posterior for beta. But this has been also widely used to develop mean-field variational base approximation for the posterior distribution of the beta parameters in probit regression. So what is mean field variational base in this probit setting? Well, again, mean field variational base and more generally variational base is one of the possible strategies that we can look at in order to obtain deterministic approximation of our posterior distribution. In particular, in variational base, what you do is you pre-specify a family of approximating densities where this family should contain tractable densities. And then within such a family, you will find the best one. So the best one is the one that lives within this family and is the closest possible to your posterior distribution under the KL divergence. So in the mean field setting, the tractability, as you can see here, is imposed by enforcing that your approximating density will factorize in some manner. So in this case, in particular in probit regression, we will take our target posterior as the joint of the beta parameter and the augmented data, and your mean field approximation will factorize as the product of the marginals for the betas and for the augmented data. So again, once we define the family, then we need to find the optimum, which will be, again, the member of this family that is closest to my posterior in KL divergence, so which means that I need to minimize my KL within such a family. Alternatively, I can also maximize the elbow. This is just minus the KL plus a constant. And for doing that, we have very simple strategies from coordinate ascent variational inference algorithm. So this is nothing but a, let's say, a recursive strategy where we optimize the approximating density for one factor at a time, conditioning on the most recent density updates for the other factors. And we do that by iterating among these two equations. So these two equations that you see here actually tell us something more. So if we focus, for example, on the one for beta, it will tell me that even if I don't specify a functional form for the density of beta, I already know that my approximating density for the beta parameter will belong to the same class of the full conditional. So if the full conditional of beta is Gaussian, we already know that the approximating density for beta will be Gaussian, and its parameter will be just obtained by updating, by serially updating, by computing this conditional expectation with respect to the approximating density of the Z variables. So by iterating throughout this algorithm, we will have that my mean field approximation for beta will be a Gaussian. The one for Z will be just a product of univariate truncated normal distribution. So again, this has been widely used and widely implemented in the context of probit regression. What we prove already is that such an approximation might start having accuracy problems, especially in high dimension. So what we prove in particular is that as p goes to infinity and n is fixed, then this approximation introduces a pretty major bias in the estimation of the posterior mean, and this then has an effect of imposing that the KL between my mean field approximation and the posterior will be always bounded away from 0 as p goes to infinity. Now, this is a negative result, but it's not extremely surprising in the sense that here we are doing asymptotics in p, not in n. So there is nothing that tells me that the KL between my mean field approximation and the target posterior should go to 0 as p goes to infinity. However, as we will see in the next slide, with our newly proposed approximation, then we will have that actually the KL will go to 0 as p goes to infinity. So what's the idea? So the idea is pretty simple. So before we have seen some accuracy problems of the classical mean field solution. So the idea is, if we want to improve the accuracy, the simplest thing that we can do is we can enlarge our class of approximating densities so that this class will become more flexible and hopefully will get closer and closer to the posterior. So the idea in which we enlarge this class is pretty simple. So what we do in particular is no more assume the mean field factorization of the two, which takes the joint for beta and Z to factorize the product of the marginals. What we came up is with what we call this partially factorized mean field family. So as you can see here, we no more assume that beta is independent from Z. So we keep this dependence within the mean field family. The only thing that we assume is that the joint distribution of the augmented data factorizes the product of the marginals. Why do we do that? Well, for two main reasons. The first one is that, as we have seen before, the optimum for the mean field has this form. So approximating density for beta and then the product of the marginal. So the optimum for the mean field live within this new class, whereas my optimum will be the best, so the closest to the posterior within such a class. So we are already guaranteed to improve the accuracy of the classical mean field solution. The other point is that we try to come up with a factorization that more closely resembles the one of my target posterior. So if we look at my target posterior distribution, as we have here, then I can always rewrite it as the product of the full conditional for beta given z and y. So given z, beta is independent from y, and then the joint distribution of the z given y, where I integrate out beta. So this one, we know it from before. It's a p-variate Gaussian distribution. The joint for the z integrating out beta can be easily derived, and it will be an n-variate truncated normal distribution with full covariance matrix. So now, if we look at the way in which the exact posterior factorizes, the only intractable part is not that much in the conditional of beta given z. The problem here is in the joint distribution for the z's, because this is an n-variate Gaussian distribution. So our idea is, let's keep the same density of beta given z. Let's just simplify the joint for z by assuming that it factorizes as a product of the margin. So that was the idea of this partially factorized mean field class. Now, as I was mentioning before, my partially factorized mean field solution will be the optimum within such a new class. The mean field lives within that class, so we are already guaranteed to be closer to the posterior in KL divergence relative to the classical mean field. The other interesting aspect is that deriving the optimum within such a new class is also similarly simple and actually has the same computational cost. So in particular, to derive the optimum, the first thing that we need to do is to exactly match my partially factorized mean field approximation for beta given z with the full conditional, okay? So that will be just a perfect matching. The only thing that I need to do now is to approximate this n-variate truncated normal distribution with the product of marginals. But to do that, we can leverage the closure under conditioning properties of multivariate truncated normal distribution, apply the Cavi equation there, and that will tell me that actually the approximating density for each augmented data will be again a univariate truncated normal distribution, whose parameters are essentially obtained by solving a system of n nonlinear equations in n unknowns, which are essentially the steps of my Cavi algorithms. So the optimization is as simple as the mean field. The other interesting aspect is the following. Once I have now the approximation for the joint of beta and z, then I need to derive the one for beta because that's the object of inference. So what we need to do is to integrate out the z from the joint approximation with respect to the univariate truncated normal approximating densities. And to do that is pretty simple because if you see here, so if you see in the full conditional distribution for beta given z, that's a Gaussian evaluated with mean, which depend on a linear combination of the z variables, which now I know that they are univariate truncated normal. So the marginal for beta is again a linear combination of a p-variate Gaussian and n univariate truncated normal. Now just recall the additive representation of the unified skew-normal. Now we have that my posterior for beta will be again a unified skew-normal distribution. But what's the interesting part now is that I no more taking linear combination of an n-variate truncated normal with full covariance matrix. I will have a linear combination of n univariate truncated normal distribution, which is way, way more tractable. So for example, now to sample from my unified skew-normal posterior, the approximation of such a posterior, I would just need to sample from n univariate truncated normal and no more from an n-variate truncated Gaussian, which is way easier. To evaluate the normalizing constant of my approximating density, I no more need to evaluate the CDF of an n-variate Gaussian distribution. I would just need to evaluate n CDF of univariate Gaussian distribution. So it's way, way more tractable from an inference perspective. Actually, what you can prove is that the all computational cost, both to derive the optimum solution and also to do inference, is essentially linear in the highest between P and N. So just some theory. So this is the one that I was telling you before. So in this case now, we can prove that as P goes to infinity, then yes, with this new approximation, the KL between this new approximation and my target posterior will go to 0. So here the idea is pretty simple in the sense that what will happen is that under random design assumption, so let me show you here. So as you can see, the exact truncated normal posterior has this variance and covariance matrix. Under random design assumption, what you can prove is that as P goes to infinity, this variance and covariance matrix will converge to the diagonal, and therefore will get closer and closer to my partially factorized mean field class, where I am assuming this factorization. So that's basically why this result happened. Of course, then now this has an impact on the accuracy, for example, in estimating the predictive probabilities that you can see here. So we can match them in high dimension. This doesn't happen, for example, for the mean field. A byproduct of this theory is also that what we can prove is that as p goes to infinity, then my Cavie algorithm essentially converges in one iteration. So the point here is that, again, since your target is getting closer and closer to a diagonal, then you no more need to solve a system of n nonlinear equation in n unknowns. You just need to solve n nonlinear equation, each one in one unknown. So let's see now if this theory is also visible in practice. So here we have an Alzheimer application. So it's a large P moderate N study. So it's presence or absence of Alzheimer's disease as a function of demographic data, genotype, and assay results. So here we have 300 statistical units, almost 10,000 inputs, because we consider also the interaction. So here we go with again, Bayesian probit regression with Gaussian prior for my beta parameter. And the first question that we ask is, let's compare the different methods in terms of runtime in this high-dimensional regime. So here you have the computational time for state-of-the-art implementation of several methods. So we have Hamiltonian Monte Carlo implemented in Stan. Here you have expectation propagation using the EPGLM package. This is sampling IAD from a unified skew-normal posterior, leveraging the additive representation. This is mean field variational base, and then you have the partially factorized solution. So as you can see, in terms of runtime, the last two are way, way more scalable. So unified skew-normal, so sampling IAD here is facing mainly problems with the fact that n is getting larger and larger. So p is not a problem because we just need to sample from the p-varied Gaussian. Expectation propagation and Stan suffer from the high p regime in this case. So here in the sampling-based method, we have 20,000 samples. So now the question is, okay, mean field variational base and partially factorized variational base seems the more scalable. Which one should I choose then for inference? Well, the most accurate one. So the one that gives me the closest approximation to my posterior. So here you see the results. So what we do here is we compute the posterior expectation of the beta parameters, the posterior standard deviation, and then also the predictive probabilities for 30 held out subjects. So we compute them via Monte Carlo using the IAD sample from the unified skew-normal posterior. So that's my target because those are guaranteed to be sampled from the exact posterior. And then I compare these quantities with the approximation that I have from mean field variational base. So these are the gray circles and the partially factorized solution, which are the black triangles. So the first thing that we see, for example, by looking at the standard deviation is that mean field variational base is underestimating posterior uncertainty. This is something that we typically know from variational base. What, however, is even more striking is in the expectation part. So as you can see, mean field variational base is overshrinking towards zero, the posterior expectation, which is something that we were claiming in theory. And this, of course, has an effect of overshrinking the predictive probabilities towards 0.5. In our case, instead, if you remember, the theory in high dimension was promising that we should have matched the actual posterior, and this seems to happen. So we're matching the expectation and predictive probabilities. We also are able to remove bias in the standard deviation. So let's now extend even more the results. So essentially what we have seen so far was for a specific model, probit regression, for a specific approximation strategy, variational base, how much we can improve the accuracy by moving from a Gaussian approximation, the one that was giving me the mean field solution, to a skew one, which was the one obtained by our partially factorized construction. When we're at this point, then our question was, well, maybe we are able to obtain, to improve the approximation more generally under more generic model and more generic approximation methods. So here the idea is that typically, like variational base, expectation propagation, Laplace method, they often give us Gaussian or at least symmetric approximation of our posterior distribution. So our question at this point was, in this general setting and for these general models, are we able to develop, let's say, a perturbation scheme of this symmetric approximation, which is guaranteed to give me an improved accuracy and no additional optimization cost, keeping the tractability? So that's the game that we will play now. So we will extend both in terms of models and both in terms of methodology. So here the setting that we start is the following. We have our target posterior distribution, P of theta given Y, and someone give us a pre-computed deterministic approximation, which is symmetric about at theta. So suppose that, for example, you already obtain your Laplace approximation to your posterior distribution, or you obtain your expectation propagation approximation, or your Gaussian variational base approximation. So I have this deterministic symmetric approximation. What I would like to do now is to perturb such a symmetric approximation in order to obtain an asymmetric one without paying additional optimization cost, but by having guarantees that the new approximation will be more accurate and similarly tractable. So that's the game that we will play. The solution is actually very simple and can be explained with this picture, okay? So the first picture is, again, in the simple univariate setting, I'm representing my posterior density, so the black one, and then I have my symmetric approximation, which is the orange line, okay? So this is something that has been already assigned to me, has been already obtained, and I know that it's symmetric about at theta. Now, at this point, the first thing that we notice, which is actually at the basis of this new idea, is that actually such a symmetric approximation is way more accurate in approximating a symmetrized version of the posterior. So in particular, this symmetrized version is obtained by taking my posterior density. For every point theta, I compute the density at that point and the density at the symmetric point with respect to at theta. I sum them up, and then I redistribute them equally to the 2 points. So that's my new symmetrized posterior, which is the one that you see represented in black in the second figure. So what we prove is actually that, again, this orange line, even if the original target was the posterior distribution, such an orange line is actually more accurate in approximating a symmetrized posterior, which is the one that we obtain here. However, again, under the total variation or any alpha divergence. So it means that this orange line will be closer to this symmetrized posterior rather than to the original posterior. Of course, I mean, this symmetrized posterior was not my goal of inference. My goal is the original posterior distribution. So this is an interesting result, but then I need to go back to my original posterior. So that's the idea, pretty simple. So what we do here is I write my posterior density as the posterior density itself multiplied and divided by the symmetrized posterior. So I can rewrite this as 2 times my symmetrized posterior times the original posterior divided by the symmetrized posterior. And now I'm done, because what I need to do at this point is, since by point 2 I know that my symmetrized posterior is well approximated by my original symmetric approximation, I can just replace it by my original symmetric approximation, and then I will end up with a new approximation to my posterior distribution, which is 2 times the original symmetric approximation perturbed with this factor here, which, as you can see, is effectively a skewing function because it's measuring the relative proportion of the density assigned to theta relative to the total density that the posterior assigned to theta and to the symmetric point. Now, what's the interesting thing here is that, again, the symmetric approximation was already derived in order to be tractable. The question is, what about this skewing function? Will be tractable itself? Well, it's ratio of posterior distribution, so can I compute it? That's the interesting part, because again, the ratio of this posterior distribution, the only intractable component will be the marginal, so P of y. So, however, I can write all of them as the joint of theta and y divided by P of y, which is the intractable component in Bayesian inference, but now this quantity will cancel out in the ratio. So this skewing function can be effectively evaluated in closed form, and you don't need any sort of additional optimization because het theta has been already computed in the symmetric approximation. So that's my perturbed version. So this is the final result. Our goal was starting from a symmetric approximation, which is this quantity here. I just wanted to perturb it to obtain a new one. The perturbation scheme is the one through this function here. Interesting aspect is that this is actually what is known as a skewing function, in the sense that it is between 0 and 1. And then the value of the function at theta is 1 minus the value of the function at the symmetric point, which means that my new skew perturbation is actually within the class of skew-symmetric distribution. So I start from a symmetric density, which I perturb in closed form. The perturbed density, so the newly perturbed approximation, will be within a known class of skew-symmetric distribution, for which, for example, I can easily sample IAD. So what I just need to do to sample from this new skew-symmetric density is to sample from the symmetric one, so from this quantity here, which is something that I know, So suppose that it's a Gaussian. And then what I just need to do is I need to evaluate the sample value at this symmetric function. If the value is below a sample from a uniform, I will keep it. If it's above, I will just take the symmetric point. That will give me values, IAD values from such a symmetric density. So here, effectively, again, we have a closed form perturbation, which doesn't require additional optimization cost, and from which I can, like, the whole computational cost is sampling from the symmetric density component. Again, this is guaranteed now for infinite sample to always improve the accuracy of the original approximating density under any alpha divergence and the total variation distance. So in particular, again, the first thing that we proved was that the very first result that I showed you, so that my original symmetric approximation is closer to a symmetrized posterior rather than to the posterior. The second thing that we prove is the result that you see down here, is that actually the error made by my new approximation in approximating the posterior is exactly equal to the error made by the symmetric approximation in approximating the symmetrized posterior. Because what we are doing now is effectively we're matching exactly the skewing factor. So what you do now is just you need to use this equality here together with this inequality on top, and this will tell you that really your new skew approximation is closer to the posterior relative to the original symmetric one. So what we actually prove is also that this skewing factor is also optimal in the sense that it's the best one that you can find within the class of skewing factor given skew-symmetric densities. So here we see some result in practice. So again, we're looking now at an application to glioma. We have almost 800 statistical units, 23 covariates. Here we look at logistic regression because now the method is more general. We no more need to constrain to probit. And what we're doing here is we compute different moments using Hamiltonian Monte Carlo, which will be our target. And then we will compare the accuracy, how much we improve relative to the symmetric approximation. So here the idea is that I have this probit logistic regression in the Bayesian setting. I will obtain the Laplace approximation, Gaussian variational base, expectation propagation, and then I will perturb each of them with my closed form solution. And then I will compare the accuracy of this deterministic approximation in approximating, for example, the different quantiles of my posterior. And also we will compute how close it is to the target posterior with respect to the Wasserstein distance, the Kolmogorov-Smirnov, and the total variation. So here you see the improvement. So any like LA is Laplace, skew LA is the skew Laplace with the closed form solution. As you can see, we're always improving according to our theory, sometimes actually by big magnitude, sometimes we even halve the error made by the original approximation without paying any additional optimization cost. Okay, so now let's go to the last part. So what we have seen is that we're always improving relative to this symmetric or Gaussian approximation. The question is how much? So can we quantify at least asymptotically how much we are improving relative to them from a theoretical perspective? And to do this, we will see a skewed extension of the Bernstein-von Mises theorem. So as you all know, in Bernstein-von Mises theorem, in short, is a theoretical result within Bayesian statistics, which essentially tells you that under suitable regularity condition, the total variation distance between your posterior distribution and a suitably defined Gaussian distribution goes to zero in probability under the law of the data. So essentially, it's basically stating the limiting Gaussian form of your posterior distribution. However, what we have seen so far is that by looking at skewed version, typically we improve relative to symmetric or Gaussian approximation. So our question is, if I replace the limiting Gaussian distribution of the BVM theorem with a limiting extension, so with a limiting skewed perturbation of such a Gaussian, will be an improvement in terms of the rate of convergence is just by, let's say, a constant, or will be by a factor. So that's what brought us to, let's say, kind of refine this statement by using, let's say, skew Gaussian distribution rather than the Gaussian one. So here is the theorem. Essentially, what we prove is the following result. So that under the classical condition of the Bernstein-von Mises theorem, with clearly some control more on the third order derivative, because here we are doing kind of higher order theory relative to the classical BVM one. What we have is that the total variation distance between my posterior distribution and a suitably defined skew-symmetric distribution has a rate, which, as you can see here, has n at the denominator, whereas in the classical Gaussian setting, you have a square root of n. So what we're proving here is effectively that we have this kind of sort of pre-limit to the BVM theorem, which says that we are converging at a square root n faster rate if we're using this kind of skew-symmetric distribution rather than the original Gaussian. And this skew-symmetric distribution is basically derived by taking higher order expansion in the Taylor expansion of the log posterior. So it would depend basically by the first, second, and third order derivative of the log likelihood and also of the log prior. So essentially, we are quantifying the magnitude of the improvement from an asymptotic perspective of the classical Laplace approximation at the end. So again, this theorem is stated knowing the true data generative parameter. To put into practice, we clearly need to estimate such a parameter. So what we tried to do was also to quantify the magnitude of the improvement in a more practical version where we replace theta naught with an efficient estimator. So in particular, what we did is we replaced theta naught with the map, so the maximum a posteriori. The skew-symmetric approximation that we have from the skew BVM has this form here, which effectively, as you can see, is the skew perturbation of the Laplace, because here I have a Gaussian center at the map with variance and covariance matrix, the inverse of the Fisher information evaluated at the map. And then this is my skewing function. So F is basically the CDF of any univariate distribution, which respects some regularity condition. Het alpha is essentially a cubic function. So here we are effectively quantifying, let's say, the improvement. And here you see, again, some empirical studies, which shows you that by, again, including such a skewness, we can have this order of magnitude improvements. So let me conclude. So it was a sort of, let's say, path along the result of skew-normal applied to Bayesian statistics. And the main message to me is that although this has not been explored too much, I think that the combination between Bayesian inference, Bayesian statistics, and this broad class of skew-normal distribution can open, let's say, several interesting directions in terms of conjugacy, in terms of improved approximation, in terms also of theory. And indeed, as you can see here, these are further extensions on which I'm working at the moment. So for example, what we're doing now is to explore conjugacy properties beyond the unified skew-normal class. So essentially, the very broad unified skew-normal result was related to the fact that basically unified skew-normal are self-conjugate. The same result can be also found in more general classes of skew-elliptical distribution. So it's not just skew-normal, but for example, skew-T, skew-Cauchy, skew-Laplace. So the question is, if we extend to this type of model, can we still recover some interesting conjugacy result? The other interesting the direction that we're exploring now is what about estimating het theta? So in the previous example that we have seen so far, the setting was that the symmetric approximation, so symmetric around het theta, was already assigned to me. So I was not optimizing with respect to het theta. I was just perturbing such an approximation condition on the fact that theta was already estimated. But again, this het theta was estimated targeting the posterior without knowing that such a symmetric approximation would have been perturbed later on. So the question is, now that I have this general framework, what will be a good estimate for theta? Intuitively, the idea will be the one that basically is better approximating a symmetric component of my posterior distribution. The best symmetric component which I can extract and which I can approximate with my symmetric family. So we are working on that aspect. Theory in high dimension, so extension of the skew BVM in high dimensional setting is interesting and challenging as well. Another aspect that we are exploring now is online settings. So this idea that can I have a sort of online updating of my skew approximation as the data streaming with time while preserving, let's say, the accuracy of the approximation the theoretical guarantees. So for example, this was motivated by reinforcement learning and bandit problems based on this kind of binary rewards and see whether we can have something which is online as new data streaming. So with that, I'm done. And I thank you for your attention, and I'm happy to take questions.
Thanks a lot, Daniele, for this very interesting talk and this quite a lot of ideas thrown off. Are there any questions from the floor? I'll start with one, but please either write in the chat or you should be able to unmute yourself. The last thing you presented, the Bernstein-von Mises approximation, with your next slide, or the one just after this one. So the approximating density, it's a valid density the one on the bottom left. It's a valid density everywhere, right? Because
Yeah.
sometimes you have these, say, like Edgeworth expansion where it's valid in some neighborhood of the mode, but it actually doesn't give you a valid density. But this one, in principle, you could sample from too, also.
Exactly. So that's actually, so I mean, you got a very important point, which was motivating us for that, because there are also, again, like higher order extension of the BVM based on Edgeworth expansion. But the point is that they are kind of stating convergence to a density which may be not valid, even not positive. In this case, actually, it's guaranteed. So that was our key, which is also the part that somehow complicates the proof as well, in the sense that it is guaranteed to be a valid density. So there, the idea basically is that, so we take this kind of higher order Taylor expansion up to the third order. And then what we notice is basically that, so we can collect the second order term to highlight the Gaussian density part, as in the classical Laplace method. The remainder is e to the power, the third order derivatives. Then what we see there is that that term has the same expansion of a CDF evaluated at that term. So we match that, and with that matching give us a skew-symmetric density, which is guaranteed to be a valid density. And for sampling, again, the mechanism is the same as before. So you just need to sample from the p-variate Gaussian, then evaluate the sample, so the skewing function at that sample, and then compare it with the sample of a uniform. So if it's above, you keep it, otherwise you change the sign. So this is a valid density everywhere. So you can also use that to do inference then.
Yeah, great. Any questions from the audience? That's all. Thank you.
Go ahead. I have
Yeah.
one question. Yeah. Thank you very much. First, Daniel, for very interesting talk. As Leo said, there is just lots of ideas in this presentation. So thank you very much for presenting to us. I have two particular questions. The first one is in the beginning when we talk about the normalizing constant for the Sun things, when you have like a probit likelihood and combined with the Gaussian prior. So I remember you mentioned about the normalizing constant, calculating it, but can you please explain a bit more how difficult it is to calculate, especially for P larger?
Okay, so thanks for the question. So here the normalizing constant will be the CDF of an n-variate normal distribution with full variance and covariance matrix. So the interesting aspect of this result is that there is no more problem regarding P. So in high dimension will work extremely well. And actually that's the part where typically MCMC faces the biggest problem. Here the problem, however, then would be translated to the large N setting, because as N grows, then so it's available in closed form, but then computing it becomes more and more challenging as N grows. So again, would be P is no more a problem, N will start becoming a problem. So in this case, again, there are very interesting recent work trying to evaluate CDF of like high dimensional Gaussian, which are very accurate until N is in the order of few hundreds. As N start increasing, then it becomes more and more problematic. That, for example, was the why we tried to come up with the variational approximation. In that setting, the interesting aspect is that the normalizing constant of the unified skew-normal that arises from the variational approximation will be again the CDF of an n-variate normal, but now the variance and covariance matrix will be diagonal. And so you can just compute it as the product of univariate Gaussian densities.
Okay, that's great. So if I understand correctly, so large P is not a problem, large N is the problem.
Large N can be the problem. Yes, exactly.
Oh, okay. And thank you. And I had another questions when you went to the variational Bayes approximation things. So it seems like you compared with the MCMC based approach, and of course there was the EBVP as well. That's part. Yeah, that's one. So yeah, so of course it's like computationally it's much faster. And in terms of accuracy, the PFM VB is better. But is there any way you the comparison between the MCMC approach? What like how was that like?
So
just
here,
wondering. Yeah.
So what will happen is, so essentially, so here we are comparing the estimate that we have from mean field and partially against IAD sampling from the unified skew-normal. So the fact that with the partially factorized solution, we are matching the moment computed IAD by sampling from the exact posterior, it means that at most stan will do equal or worse, right? Because we're already in the moment of the exact posterior here. So the best thing that sun can do is to match the moments of the sun. Maybe yes, maybe sun will approximate a bit better the standard deviation. Here we are removing at least the bias. But again, we decided to compare just these two because I mean they were like feasible from a practical perspective, whereas here it was taking much more time because this is the problem with the large P part.
Right. Okay. I think I got it. Yeah. Thank you so much. Thank you.
Florian, did you have a question?
Yeah. Thanks, Daniele, for the great talk. I have to say, like when I read the abstract, I felt like, how is it possible that you can like stack so many ideas in one talk? But I mean, it was really interesting. I guess I may have missed something, but I think one part that I found particularly interesting was about the optimality of the skewing function, because I'm not sure if I grasped fully what you meant by yeah, exactly, like around yes. So basically you're gonna skew the sort of like, what is Q bar already?
So this one here?
Yeah.
This is the symmetric approximation that I already have. So think about the Laplace approximation that has been already obtained.
Right.
So I'm forced to keep that. So at the moment, they say I'm forced to keep that. The only thing that I can do is to perturb it in some way.
Yeah. And which you looked, so what's your optimality criterion then to say that this is the best you can do?
So it's related to this part here. So here the thing is the following. So the idea is it's optimal in the sense that I would like that it remains a skewing function. So in the sense, the point is I could perturb like my symmetric density in many ways, right? So here what I want to do is to perturb that in a way in which then the resulting skewed approximation that I get is also tractable from an inference perspective. So to be tractable, then my new skew approximation needs to live within some class from which I know how to do inference under that class. And for example, the class of skew-symmetric distributions is one of those because, again, if I know that this belongs to the skew-symmetric distribution class, then, for example, I know how to sample IAD also from my new perturbed version. So here the question is the following. Which function should I use to perturb such that, so it's optimal, let's say, within the class of function, which guarantee that I stay within the skew-symmetric class. So the point is, if I force my skewing function, the skewness-inducing mechanism to be a skewing function, so that's specifically related to the terminology of skew-symmetric distribution. So it's a skewing function if it's in between 0 and 1. And then basically if it behaves like a CDF, in the sense in between 0 and 1, and then the skewing function at theta is 1 minus the skewing function at the symmetric point. So the idea is that if I optimize within such a class of skewing function, then the best thing that I can do under the total variation, the alpha divergence, is to use this skewing function here. So this will be the one that guarantee me that I obtain a skew distribution that is the closest possible to the posterior while being forced to live within the class of skew-symmetric densities.
Okay, so it's regarding the total variation and any alpha divergence, basically.
Yeah, it's with respect to that method, yes.
Okay, very interesting.
So essentially here the proof is by contradiction. So we say, suppose that there exists something better, and then we do the derivation and must be this.
Okay.
Okay. Better. So, or if it's better, then it's no more within the class of skew-symmetric distribution. So that's
and it holds for any theta hat, basically. For any
yeah. So you're given a posterior which is symmetric at any theta hat, or semi. That's the point. Then the quality of the overall approximation, that's the key result here. Theta hat must be chosen in a meaningful manner because, again, then the quality of your final skew perturbation will be basically the quality of your symmetric one in approximating the symmetrized posterior. So if you find a theta hat, which is very good in approximating the symmetrized posterior, then your final approximation of the posterior through the perturbation mechanism will be extremely well. So that's the point why, for example, we would like also to optimize with respect to theta, because originally theta is developed to approximate well the posterior. But now with this new idea, what I should do is to pick up at theta to approximate well not the posterior, but the symmetrized posterior, because then I will perturb it later on. So that's the thing where we're working on now.
I see. Maybe just another quick question. It was when you were presenting the ideas with the CAVI algorithm, it seems like everything was very clever, but it seemed to me that it was applicable only in situations when you have like this kind of latent framework, like latent variable that you can use. So obviously, I guess like you presented it in like in a general like latent variable framework. Can you go beyond that, you think?
So that's a good question. So this work is very specific again to the variational base applied to probit regression and more generally to models which admit conditionally conjugate representation. So typically, again, CAVI is very useful in those regimes where you have it works well essentially in all those regimes where you give sampling works well and can derive easily. Then you know that also mean field variational base with CAVI can be done in a simple manner. If you go beyond that, it becomes more complicated because again here, for example, if you don't have closed form full conditional, then computing the expectation become problematic. So in that case, you go mainly with gradient methods and extension of variational base. But again, CAVI is very specific to this kind of setting, so it typically works well in that case. So that's also why we wanted to kind of go beyond also that idea, like in this perturbation scheme, the final one that we propose here, it's very general. So you don't need require this kind of augmented data representation or conditional conjugacy. Any method that gives you a symmetric approximation, then we will perturb it afterwards. So the way, I mean, you can also come up with your own symmetric approximation just by looking at the data. So it doesn't care. I mean, of course, then the quality will depend on that, but then the scheme is how we optimize.
Right. And if you had the choice, for instance, in a probit like model to do either approaches, is there one that's more compelling than the other?
So actually, we were kind of comparing for the mean field variational, so the partially factorized construction with this new idea. So in terms of general implementation, like the thing that we have seen works best is the skewed version of expectation propagation. Because the expectation propagation is already very strong in the symmetric setting because it matches the first and second moments. So it's very good in capturing the location and the variability of your posterior. That gives you enough variability to perturb that well. So what we have seen is that generally expectation propagation combined with our perturbation scheme is very difficult to beat. In terms of the mean field, so the partially factorized with this construction, it depends a lot on the regime. So if we are in a regime where P is very large, which was the regime in which the original one was constructed, that's very strong. The partially factorized construction. If we are in a regime where P is not large relative to N, then probably it's better to have like the skew perturbation of expectation propagation. So that's depend a lot on the regimes. But in like the thing that we have seen, it works best in essentially many different regimes. It's very difficult to beat is the skewed version of expectation propagation. It's very strong.
Thank you. There's a lot of things to think about. Thank you.
Thank you.
Yeah, thanks again, Daniele. The table where you had the results comparing the logistic MCMC with the quantiles, were they relative to the values? Or were they absolute difference?
This one? Absolute.
Yeah. Okay, absolute. So I don't know what the target exactly was, but it seems like you definitely do better than...
Yeah, you do always better. The magnitude depends a lot. Like, for example, again, if you see here the mean, we don't improve AP because AP is already centered at the mean.
Yeah.
So we're already happy that we don't do worse because by doing some perturbation, then you may induce some bias on the mean. However, overall, like you tend to sometimes you always improve, sometimes you tend to halve, depending clearly on the distance that you use. But the key thing here is that this improvement come at no cost, right? Because you don't need to optimize anything more. And at the same time, you like sampling is the same cost as sampling under the symmetric because then it's just a sign change.
Yep. Have you ever done a comparison with INLA?
No, but we would like to do that. So actually in the skew BVM, we have also results for the marginals, which actually could be used within INLA as well. So we haven't done a comparison with INLA. We would love to do that. And also we would love to explore potentially including, because INLA uses a plus approximation to a certain
to the denominator,
The point is, if I replace that with the skew one, which I can still integrate numerically in closed form because the skew one now, the CDF part is univariate, so it's very cheap. Maybe I can improve even INLA as well.
Yeah, but I think even nowadays, Harvard is working on having
Yes,
skewed
yeah, Harvard
approximations.
includes some. Yes, yeah, yeah.
So I don't know whatever the software has as a current version.
I
Thanks
guess
a lot once again for
yeah.
for this. In the interest of time, unless other people have question, I'll thank you all for attending the talk, and thanks once again, Daniele, for the fantastic presentation. If you have questions, feel free to stick around maybe a couple of minutes. Otherwise, see you next week for another colloque des sciences mathématiques du Québec. Thanks all.